In this video, I'm going to introduce you to the two most fundamental quantities we use when we describe a fluid. These quantities are density and pressure. Let's begin with density. To get started, let's look at this chunk of material here. This chunk of material could be anything. It could be a solid, it could be a liquid, it could be a gas. But anyway, let's say that this material has mass m and occupies volume V. We can then introduce the density of the material. The density is denoted by the Greek letter rho, and the density is, by definition, the ratio of the material's mass to its volume. Based on the units which we use most frequently in this class, the unit of density could be then kilograms over meters cubed. Kilogram is the unit of mass we use most frequently. Meter is the unit we most frequently use for length. So then meters cubed would be our standard unit for volume. However, in this topic, we also tend to use what are called the CGS units, which are based on centimeters, grams, and seconds. So if we are using the CGS units, another unit we could use for density is grams per cubic centimeter. Now that we have the units, I can give you values for the densities of some common materials. Liquid water has a density of about 1 gram per cubic centimeter. Aluminum has a density of about 2.70 grams per cubic centimeter. And gold has a density of 19.3 grams per cubic centimeter. Let's do a quick example calculation. Let's say I have an aluminum cube, which is 2 centimeters on each side, and we want to find the mass of this aluminum cube. So here's what we do. Let's go back to the definition of density. We have that density is mass over volume. So we're just going to solve for mass. Mass equals density times volume. So we're just going to substitute, put in the density of aluminum, 2.70 grams per cubic centimeters. The volume of a cube, which is 2 centimeters on each side, would be 8 cubic centimeters. So cancel cubic centimeters against cubic centimeters, and we get that the mass of this cube is 21.6 grams. Now let's move on to pressure. To get started here, we'll have to use our imaginations a bit. Air, of course, is a gas made up of many tiny air molecules just zooming around all over the place. So let's say then that I take this 3x5 card and insert it into the air. What's going to happen? Well, just imagine all the air molecules in this region over here. They're going to start pounding onto this one side of the 3x5 card. And what is the effect of all of those air molecules pounding onto that one side of the 3x5 card? The effect is going to be to exert a force on that side of the card, pushing it to the left. Now, of course, if we look at this other side of the card, there are air molecules over here as well, pounding into that other side of the card. But in our discussion going forward, we're going to focus on those air molecules over here on the right, pounding into the card, exerting a net force to the left. Now I'm going to sketch out the scenario that I was just acting out for you. Let's say that this is the 3x5 card, and let's say that the area of the 3x5 card is capital A. And now let's think of a whole bunch of air molecules coming in, striking the side of the 3x5 card, and then bouncing off. The net effect would be to exert a force on the card. The force that all of those air molecules exert on the card would be perpendicular to the face of the card that they are beating on. So coming to the picture here, I'm going to put in a force vector which represents the net effect of all of those collisions of air molecules coming in and bouncing off the card. So to sum up, we have this card, surface area A, bunch of air molecules coming in, striking the card, bouncing off. The net effect is that all of those collisions exert a force on the card. Now, suppose I would ask you if that force has anything to do with the properties of the air itself. Well, of course, the force has something to do with the properties of the air itself, right? If the air molecules are moving faster, they're going to hit the card harder, and that force is going to be bigger. Or if the density of the air molecules is greater, there's going to be more air molecules over here, so we have more collisions with the card, and the force will be greater. On the other hand, is the strength of that force determined only by what's going on with the air molecules? The strength of this force is not determined entirely by what's going on with the air molecules. Here's why, right? Let's say this is my card again. So think about the air molecules feeding into the card, exerting a force on it. But now let's say that the card was twice as big. If the card was twice as big, it would intercept twice as many air molecules, and the force would be twice as great. So the strength of the force is not determined entirely by what's going on with the air molecules. The size and shape of the card also matters. So what quantity could we come up with which is determined entirely by what's going on in the air itself? Well, how about the ratio of the force to the area? To illustrate this, let's suppose that I make my card twice as big again. If I make my card twice as big, then of course the area is now twice as big, but the card is now going to intercept twice as many air molecules, so the force is going to be twice as big as well. So even though the area, of course, depends on the area, and the force exerted on the card depends on the area, the ratio is independent of the area. The ratio of force to area depends only on what is going on in the air itself. It has nothing to do with what surface I stick into the air. So this ratio is an important quantity. We're going to give it a name. We're going to call it the pressure. The symbol we use for pressure is capital P, and it is defined to be the force per area exerted on a surface which is inserted into a fluid. There are several units of pressure which come up in this class. The one we're going to use most frequently is what's called the Pascal. The symbol for Pascal is PA. Now, if the Pascal is part of the MKS system, what would that have to be? Well, the unit of force in the MKS system is the Newton. The unit of area in the MKS system is meter squared. So Pascal, our MKS unit of pressure, is newtons per square meter. The other unit of pressure which comes up in this class is the atmosphere. When we use the word atmosphere to refer to that specific unit of pressure, then the symbol for that is ATM. The atmosphere is based on the global average of atmospheric pressure at sea level. And based on that definition, it turns out that an atmosphere is 1.013 times 10 to the 5 pascals. In other words, the typical air pressure at sea level is about 100,000 newtons per square meter, which is quite a bit. For the sake of familiarity, I'll also point out that an atmosphere is also about 14.7 pounds per square inch. as a quick example calculation, let's calculate the force that air pressure is exerting right now on the top face of this 3x5 card. For this, we can just go to the definition of pressure over here, and then solve for force. So we can write force equals pressure times area. Now I'm pretty close to sea level as I'm recording this video. So the pressure in my room is about 1 atmosphere, or about 14.7 pounds per square inch. So I will put that into the formula here. The area of the card is 5 inches times 3 inches, which would be 15 square inches. Square inches cancels square inches. So punching that into my calculator, I get 220 pounds. So according to this calculation, air pressure is pushing down on this card with a 220-pound force. But look at how I'm able to hold this card up just at the very end of 2 of my fingers. I don't even need my thumb, right? I could even use my pinky finger there. How am I able to support this card against 220 pounds of air pressure just using my 2 weakest fingers like that? Well, of course, we also have 220 pounds of force from air pressure pushing up on the bottom. So all I'm really doing is supporting the card against the downward pull of gravity, which of course is nothing like 220 pounds. So now I have given you a brief introduction to density and pressure. So in the next video, we can use those concepts to begin developing our understanding of fluids.